to speak about some of my work on developing these quantitative ecological state keys and how they could provide insight into structural and functional ecosystem changes. I also want to thank my co-authors for their contributions, along with the BLM, NRCS, and the Jornada Experimental Range for supporting this work. So ecological site descriptions use the multiple steady state concept to characterize ecological processes and alterations to ecosystems structure and function over time. Primary method of representing this multiple steady state concept is a state and transition model. Here's an example from the Sandy ecological site from MLRA 42, which I will be discussing throughout this presentation. In this example, the underlying ecological processes may be altered, leading to a shift in ecosystem structure and function by way of the transition pathways shown here. These photos represent the reference black grama grassland state and the altered shrubland state for the Sandy site. We can see the dramatic change to ecosystem structure, which then impacts ecosystem function. For the Sandy site, this shift in ecosystem structure can be measured using discrete species cover indicators that signify the underlying changes to ecological processes. For this site, black grama, bunch grass, and mesquite cover are the main indicators of ecological state. The objective of this work is to develop quantitative keys that can be used to classify standard monitoring data sets to ecological site and state, and use erosion prediction tools in conjunction with the landscape data commons to link erosion indicators to state transitions and management practices in EDIT. We developed the state keys using these species indicator thresholds from the published ecological site descriptions, expert and local knowledge, or other published sources to classify monitoring plots to specific ecological states through an R workflow similar to what Ali just presented. The resulting classifications to ecological state were then validated using photos of the monitoring plots where available. This validation allowed for refinement of the quantitative keys where plots may not have been classified cleanly or properly. Once classified and validated, the ecological state designations can be used to explore the relationships between ecological state and other indicators of ecosystem structure and function. I'll be focusing primarily on wind erosion estimates from the Arrow wind erosion model, specifically horizontal flux, or the amount of soil moving horizontally across the site, along with the canopy gap structural indicator. So this figure shows how the ecological state and horizontal flux from the Arrow model are related. For the Sandy site, state 3.2 seems to be at the most risk of wind erosion. Here I'm showing gap cover greater than 100 centimeters along with horizontal flux and their relationship, with the colors here representing the ecological state. Again, the state 3.2 appears to show the highest erosion potential. Now I'm going to shift over to the next example using the gravelly ecological site in MLRA 42. This site has a shrub savanna reference state, and transitions to other states are characterized by densification of shrubs and loss of grasses. This state key also relies on species indicator thresholds taken from the ESD, expert and local knowledge, and other published resources. Again, black grama is a key indicator, but also creosote bush, bush muley, and total perennial grass cover are also indicators of changes in state. Photo validation was done again for the plots associated with this ecological site, and here we see one from the reference state phase 2 and from the shrubland state phase 1 here. All right, again, we began by exploring the relationship between horizontal flux from the Arrow model and ecological state. There does appear to be a relationship where erosion estimates increase with site degradation for the gravelly site. And then we explored the same relationships between horizontal flux and gap cover greater than 100 centimeters. We see a similar relationship to that which we observed for the Sandy ecological site, but here states beyond 3.1 seem to be the most susceptible to wind erosion. So what does this mean in a management context? We can start to examine management goals and benchmarks at the ecological state scale, along with the broader ecological site level information. It can allow for a better understanding of trade-offs when managing for multiple objectives that rely on multiple indicators. As we move forward with this work, we are going to expand the exploration of these relationships to more sites in New Mexico, specifically the Rio Puerco watershed, to see if this process and workflow can be applied in areas where less information about specific ecological thresholds is available. We also hope to look at water erosion estimates from the rangeland hydrology and erosion model and other ecosystem function indicators within the context of ecological state. So thank you all for listening, and thanks again to my co-authors and the BLM, NRCS, and Jornada Experimental Range for their support. Thank you all.